Hello and welcome to lesson 13 of this Introduction to Probability of Wolfram. The topic of this lesson is the binomial distribution. Let's begin. So far, you've learned about Bernoulli trials. What happens when you count the number of successes out of a group of Bernoulli trials? Well, you would get a binomial distribution. This is closely related to the Bernoulli distribution, as it also appeared in The Art of Conjecturing by Jacques Bernoulli. In this lesson, you'll see how to compute a binomial expectation, probability, estimation, and simulation. Let's say a coin follows a Bernoulli distribution with the probability p of getting heads. What happens when you flip that coin n times? Well, the coin would be heads I times and tails n minus I times. If you remember lesson 2, this means that there are binomial ni ways of getting these successes. The probability of getting heads I times is p power I, and inversely, the probability of getting tails n minus I times is 1 minus p power n minus I. Putting all that together, you get binomial of ni times p power I times 1 minus p power n minus I, the PDF. So that's the PDF, but what about the CDF? Well, if you want the CDF, you'll have to use the beta regularized function, as this is a sum that cannot be easily reduced. You can plot the binomial distribution using your own function, as done here with the PDF, or use the built-in binomial distribution function, as done here with the CDF. The binomial distribution is just n Bernoulli trials added together. So since the mean of the Bernoulli distribution was p, the mean of the binomial distribution is n times p. And same for the variance. Since the variance of Bernoulli was p times 1 minus p, then the binomial is n times p times 1 minus p. The binomial distribution is the most frequently used discrete probability distribution. So when is it applicable? You should only use it when the event is discrete in a discrete sample space, the probability p is constant, meaning it does not change. Finally, and most importantly, it's used when each trial only has two possible outcomes. Now it's finally time to use the binomial. Let's say you flip 20 fair coins. What's the probability you get exactly 9 heads and so 11 tails? Just take the numerical probability at 9 of 20 coins at probability 1 over 2, and you get the answer. Imagine Stephen didn't study for his physics exam and decided to randomly guess all the answers. If the exam has 20 multiple choice questions with 4 answers each, what's the probability that he gets at least half of the questions correct? Well, just use the numerical probability at equal or greater than 10, with 20 at a probability 1 over 4, and you'll get the answer. Let's do a harder question. You're having a snowball fight with your friend. You have a better aim than her, as you hit her once every 2 throws, while she only hits you once every 7 throws. But you're a bit slower than her. By the time you throw 20 snowballs, she has thrown 25. To encourage her to play and to make things fair, you decide to gain 1 point and her 3 points for every successful throw. The winner is the one that has the most points. Who is expected to win? Okay, so there's 2 binomial distributions with probability 1 over 2 for you and 1 over 7 for your friend. To track the score, you can count the difference between your points and your friend's points. If the difference is positive, you expect to win, and if it's negative, you expect to lose. In that case, on average, you lose. You gave her too much of an advantage. Did you know calculating probabilities can help you avoid jail? Okay, let's see the scenario. Let's say you're accused of a crime you didn't commit. You have 3 possible trials. A private trial with 5 experts that have a probability of 0.75 of declaring you not guilty, then a standard trial with 13 members that have a probability of 0.67 of declaring you not guilty, and then finally a public trial with 41 citizens that have each a probability of 0.6 that they would declare you not guilty. Assume decisions are made by majority rule. What type of trial would be most likely to result in the right decision, that is, for you to be declared not guilty? Just make a table of the probability the number of jury voting not guilty is the majority, then calculate that probability for every single jury type. And so you see the last jury is the best, as the number of participants makes the variation decrease in general. What about simulation? Use the random variate function on any binomial distribution to sample your points. You can visually aggregate your points using the histogram, setting the plot range to see the absolute frequency, and allowing variation over the parameters with manipulate. And now you have a nice random binomial distribution that clearly sets a trend as n increases. Some of you might be skeptic. How can a coin flip have such a complicated behavior? Okay, I'll prove it to you. First, generate 100 coin flips with 20 coins, where each number is the total number of heads out of 20. Aggregate the data and normalize the frequency. Then estimate the distribution and visualize the estimated distribution against the data. And so you can see both the data and the estimated binomial distribution agree. So what should you remember? A binomial distribution describes the probability of I successes out of n Bernoulli trials. You should use the binomial distribution, probability, expectation, random variance, and estimated distribution to solve any problem based on many two-outcome trials. However, the binomial distribution is limited to discrete sample spaces. For a continuous sample space, the Poisson random variable is needed. This will be covered in the next lesson.